All right. So energy is always conserved. All it does is change from one form to the other. So you saw that in the two labs we did. The first one on conservation of energy, we were showing how energy is conserved as far as heat goes. Um, and then the one we did yesterday, we were looking at kinetic versus potential energy. So the different forms of energy, we have mechanical, electrical, thermal, and nuclear. Those are our different forms. We deal mainly with mechanical. Okay. So that's where your kinetic and potential energy comes in. That's the mechanical. Anytime work is done, energy is transferred from one form to another. It's never lost. Okay. It's always there. It's just, is it usable? And in what form is it? Because that's where it will change forms and it might not be usable anymore, but that doesn't mean it's lost or destroyed. Okay. So one process might transfer kinetic energy into electrical potential energy, or vice versa. Another might transform a spring's potential energy into kinetic energy. So if we have something attached to a spring and we let it go, that spring has potential energy, and then when we let it go and it reaches its farthest distance, we're converting from potential to kinetic. Okay. But no matter what the process is, here's the important thing to remember: the total amount of energy in the universe remains the same all the time. Okay. To say that energy is conserved means that it can never be created or destroyed. It only changes forms. Okay. And that's where we get the first law of conservation of energy from, because we just change forms. We don't lose it. We don't create it. Okay. It's not created and it's not destroyed. All right. When frictional forces act on a system, like a car's brakes being applied, that is where we are turning kinetic energy into thermal energy. So when you slam on those brakes, what you're doing is you're using friction to slow down or to change kinetic energy, to slow it down, to reduce that kinetic energy. Of course, it's not lost. So it gets transferred from kinetic energy to heat energy. So heat builds up when those brake pads are applied. Um, in a situation where forms of friction can be ignored, no potential or kinetic energy is transformed into thermal energy. So in yesterday's lab, you saw there was a little box for you to check for thermal energy. Um, and it only applied, or you only saw that bar in your graph when you added friction. So if you assume that there's no friction, you're not going to have any thermal energy. It's just going to go from potential to kinetic and back and forth. So, with that being said, in here, we pretty much assume that everything is on a frictionless surface. We're not going to try and incorporate that, which means that your total energy is going to be equal to your potential energy plus your kinetic energy. So, make sure you have that down somewhere, because that's the key to remembering how to do these problems, is that kinetic energy plus potential energy equals the total energy of the system. Okay. So mechanical energy. So mechanical energy is conserved. So whatever you had before, you have to end up with that much. It can change between kinetic and potential, but the total has to stay the same. All right. So here's an example. Energy conservation can be used to solve problems. So, for example, energy conservation can be used to find the final speed of pretty much anything that's dropped from a particular height. They use the example of dropping your car keys. You could drop anything and it's going to be the same thing. So, if you look at the graphic, the potential energy, so potential energy is greatest when you are highest above the ground. And at that point, your kinetic energy is also equal to zero because you haven't let it go. Okay? So that means your kinetic energy has to be zero. Your potential energy is always just the mass times the gravity times the height, all the time. All right? So if we drop them from this height, whatever height that is, when it lands on the ground, you have zero potential energy, but your kinetic energy is 1/2 mv squared. Okay? So what they do is they set these two things equal to each other. So your initial potential energy plus your kinetic energy, which is zero, has to equal your final potential energy, which once it hits the ground is zero, plus your kinetic energy, 1/2 mv squared. So basically it's mgh equals 1/2 mv squared. Okay, now you don't have to walk through this process every time because it'll be the same for this whole situation. So if we solve for V by dividing by 1/2 m, V squared, my m's cancel, V squared is going to be 2gh, and then we're going to take the square root of it. Okay, so V final is always the square root of 2gh. If it's something is just dropped and it hits the ground. Now, if our bell ringer had said what was the final speed of the rock once it hits the ground, we wouldn't have had to do all that other stuff we did. We could have just plugged into this short little equation and found VF, and no problem. But because it said what is it at 5 meters, which wasn't when it hit the ground, we had to go through all that other mess. Okay. So if it hits the ground, the final velocity is always just the square root of 2 times gh. All right, so conservation of energy moves that objects move down through the same vertical distance but following different paths will have the same final speed. So whether you're going straight down a slide into the pool or whether your slide curves, it doesn't matter. It just matters that the height, how high above the pool you are, that's the only thing that's going to determine your final speed. Okay? Changing the initial speed of a downward moving object by a small amount can result in a large increase in the final speed. Why would that be? Why would changing the speed just a little bit make such a huge difference in the final speed of something? So the example over there shows you have an initial speed of 4 meters per second in case 1, but in case 2, you increased your speed to 5 meters per second. And that way he went from having a final speed of 0 to having a final speed of 3. Why did it change so dramatically?
Theoretically, you put more energy in, so you get more energy out.
Yep. And kinetic energy, what's the formula for kinetic energy? V what? Squared. Your kinetic energy is 1/2 V squared. So you will have a bigger jump because you're squaring that velocity. It's not just a direct relationship, it's a square relationship. Okay? Guys, let's work on physics and hold math till math, please. All right. Okay, so let's do the example problem that is on page 208. Oops, nope, that's not what I want. It's 6.1, 613. Okay. So in this one, in the bottom of the ninth inning, a player hits a 0.5 kilogram baseball over the outfield fence. The ball leaves the bat with a speed of 36 meters per second, and a fan in the bleachers catches it 7.2 meters above the point where it was hit. Assuming the frictional force is ignored, find the kinetic energy of the ball just before it is caught and its speed just before it is caught. Okay, so once it's caught, it doesn't have any speed anymore, does it? All of it's, it's done. Okay, so we're going right before it's caught. So you can see we sketched the ball's path. So it's going up. Oops. It's going to go up, and then it's going to be caught by this person right here. Okay. When that ball is hit with the bat, it is a projectile. We did a whole section on projectiles, and they always make this path going up, and then they will come back down. Okay. So notice that we're measuring the height relative to the point at which it was hit. Okay. So this would be the 0 point. Okay. And your height is going to be wherever that person is, that person's height above the ground, which turns out to be 7.2 meters. Okay. So initially it has a height of 0, and the fan is at a height of 7.2 meters. Initially, the ball's speed is 36 meters per second, and its final speed is what we're looking for. So what is it right the second before it hits the guy's glove or hand or whatever? All right, so this is going to be your basic equation that you're always going to wind up using with these problems. It's what we used this morning. The potential energy initially plus the kinetic energy initially equals the potential energy final plus kinetic energy final. All the time. Yes, ma'am.
Why do they always ask us to find the kinetic energy first? If it's easier to find speed.
In that particular example that you did this morning, I thought it was easier to find the speed. This one might be a little bit different.
Okay.
Yeah. Because, it's going to be different because we're not looking at its height in mid-path. We're doing it at the end of the path. Okay, so, and once we know the final kinetic energy, we can then determine the final speed. Okay. All right. So, initial potential energy is 0 because it's closest to the ground, or we're going to say it's at the ground. So our initial potential energy is 0. It has no height above the ground. Okay, so remember, this is what we're basing things on. MGHI plus 1/2 MVI squared equals MGH final plus 1/2 mv final squared. Okay, so at the beginning, it has no height. So that whole thing falls out to 0. Okay, so I'm just plugging in for kinetic energy, initial kinetic energy. Okay, at the end, my final potential energy is mgh. So they just plug in 0.5 times 9.8 times 7.2 meters, because that's how high the guy is when he catches it. And we get a potential energy of 11 joules. We have an initial kinetic energy of 97 joules. Okay. All right, so our final kinetic energy, we don't know yet. Okay, that's one of the things we're looking for. So we're going to plug these numbers in. 0 plus 97 equals 11 plus whatever the kinetic energy is, because we don't know it. So that would be like our x, okay? And then we're just going to rearrange to find the final kinetic energy, and that gives us 86 joules.
Okay, I guess I have a question.
Yes.
If it stops.
It's not stopped yet.
Oh, right before it's caught.
Right before it's caught.
We talked about that.
Yeah.
Like,
And that's, yeah. And that's what may trip you up on a test. So be careful when you're reading the question that you read, is it right before it's caught or is it after it's caught and it's stopped?
Okay, and if it is caught, then kinetic energy is 0.
Then it doesn't have any kinetic energy, exactly.
Then is it potential from the caught, and then when you, or from before it was thrown, and then when it's caught?
That's your only, yeah. Oh.
Well, I guess.
The kinetic energy it had right after it was hit, the 97, would have to equal the potential energy it has once it's caught.
So, like, when we did that little thing and it went back and forth, so does that mean, like, the potential energy?
All the kinetic energy turned into potential energy.
Okay, so it doesn't really, like, go back and forth. It's like a process, maybe.
Yes.
So it slowly becomes
right.
Potential.
And if you go back and look at that FET simulation, as the skater's going, choo, choo, it's going, nee, 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 until she finally stops, and then it goes back to one or the other. Okay. All right. So then we're going to use this 86 joules, and we're going to plug in, and we're going to solve for VF. Okay. So that would be 86 equals 1/2 times, what's the mass of the ball? 0.15 times v squared. So again, we would then 0.5 times 0.15. So 86 equals 0.075 v squared. We divide both sides by 0.075. V squared equals 1,146.7, but then we take the square root. We can't forget to take the square root. And it's 34 meters per second. Okay? So any questions on that? Okay, let's do this. Let's try to work out problem number 38. So on that same paper that you did your little bell ringer on, just try and work out problem number 38. The answer is supposed to be 5.7 meters. Are we? That's what you got to figure out.
What was the answer?
5.7. Something.
Is it okay for like a few decimals off?
Yeah, your decimals off is okay. What did I? Let's see. Yes. Unfortunately, I am not a perfect person. And seeing as how I have not worked this problem out before, I may have made a mistake. My formula is not a mistake, though. That is the correct formula. I plugged something in wrong. Okay. Let's see. I bet I can't cancel those out. Okay. Oh, that's right. I can't cancel those out. All right, everybody done? Yes, I would like for you to turn them in. So I'm not going to finish it out at this point because I want to see what y'all have done.
I got it right on the dot, big dog.
If you plug in to all of that and solve for what? H. You'll get it right. I made it an algebraic mistake and tried to factor out something and cancel something that I should not have tried to cancel out.
Initial H0.
Yeah, you're supposed to make the initial H0 because that is the 0 point. And so that whole term falls out. No, just turn in the actual paper.
Oh, well, no. Are you going to give us this for homework?
There are some homework problems in Schoology. I think it's 41 and 44 and 45,
Oh, okay.
I believe. You'd have to check Schoology to be sure. But it's not this actual problem. And even if it is, I'll have the paper, so you don't have to redo it. We've already done it.
Okay, quick question.
Yes.
So I did it that way and I got 5.7. But then all of a sudden I go, I'm curious, can I do it this way? And so I plugged it into the VF is equal to the square root of 2 times G times H or whatever. Because I wrote down when the object hits the ground. You said something like that. But that didn't work. You gave me like 7.
Right.
So when do I use that? Because I think I might have
If it's just dropped.
Oh, okay.
Yeah.
So it's not thrown. It's
Not thrown, it's just dropped.
Okay, cool.
Yeah, and it actually hits the ground. So. All right, y'all are dismissed. Check Schoology for the other practice problems that you need to be working on, and we'll go over them tomorrow. Are there any stairs in this building? Stairs. Do we have any stairs anywhere on this campus? Outside where?
Library.
The library has stairs?
Outside of it.
Oh yeah. I mean a real flight of stairs, not 4 stairs.
Back at Fieldhouse. That's like 4 stairs. No, it's not. It's
I mean, you could use the bleachers.
Yeah, I think we'll have to use the bleachers. We may do that.
Chandler Dawson, Ashley Zane, Ty Parker, Abigail